Okay, hello everyone in a new video. So we have reached part 7 of chapter 8, which is the chapter of Newton's second law for rotation. Now let me start with the section number 3, which is the moment of a couple. Now here by couple it means a pair. So it is two things at the same time. Now let me here consider a rod of extremities A and B, and let me suppose that this is the positive direction. Now suppose here that the rod can rotate around an axis delta, but I didn't specify the position of delta, so the axis of rotation may be here, 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 or even here. We don't know. It's something somewhere between A and B. And at the point A we have a force F applied like this. Now let's say that this is the force F1, and we have another force applied at the point B. But now notice the following, that the force F1 have a line of action which is oblique and direction upward to the left. Now we will apply at the point B a force given by F2. So first let me do it this way, just to be clear. So now this is the force F1, and this is the force F2. Here I have represented F1 and F2 in a manner just to stress that F1 and F2 are opposite. And have the same magnitude. Okay. Then in this case, F1 and F2 form a couple. So F1 and F2 form a couple because they have the same line of action, opposite direction, and same magnitude. Okay. So for example, here you can consider this is the tangential direction. If the radial direction something like this, then this is the tangential direction, and this is the tangential direction. So this angle here, theta, will be equal to this angle, theta. Okay. So in this case, F1 and F2 form a couple. Then we know that the sum of moments acting on the rod due to F1 and F2 is equal to the moment of the force F1 around the axis of rotation delta plus the moment of the force F2 acting without the sum of moments. So this can be calculated in an easier way, which is equal to the moment of the couple and between brackets, because F1 and F2 form a couple, and instead of calculating the moment of the force F1 and the moment of the force F2 separately, one can directly calculate the sum which is given by the moment of the couple. So the moment of the couple in this case is simply given by either the magnitude of F1 or F2. So in this case, because F1 and F2 are equal in magnitude, so we can say that F1 is equal to F2, is equal to the magnitude F. So here we have F tangential multiplied by the distance D, here in which distance D is equal to AB, which is the distance between the point of application of F1 and the point of application of F2. And as you can notice that in this case, whenever we are talking about the couple, the distance T represents the distance between the point of application of the force F1 and the point of application of the force F2. Whereas if we are talking about the moment of the force F1 alone, it's given by F1 tangential multiplied by the distance D. In this case, this distance is the distance between the point of application of the force F1 and the axis of rotation. Now what's nice about this formula is that independent of the position of the action of the axis of rotation, one can calculate the moment of the couple just knowing the magnitude of the forces. In this case they are equal for sure because we are talking about the couple, and the distance D. In this case the distance D is only the distance separating the forces F1 and F2. So these two forces that form a couple, they have a sum of moments independent of the position of the axis of rotation. Okay, so this only happens if the forces F1 and F2 form a couple. So if you want to give an example on that, now suppose here we have a rod AB, and the length of AB is given by 1 meters. Now we have a force F1 applied like this, and we have another force applied like this. So, and we are interested in calculating now the axis of rotation somewhere here. Okay, so this is the point, say for example O, and this is the axis of rotation, and we want to calculate the moment of the force F1 on delta plus the moment of the force F2 on AB passing through delta. So this is equal to how much? Now in order to calculate each one, we can say that the moment of the force F1 over delta is equal to F1 tangential multiplied by the distance T, but in this case the distance T is equal to AO, but we don't know AO. Similarly, if you want to calculate the moment of the force F2 on delta is equal to F2 tangential multiplied by the distance D. D is equal to the distance from the point of application to the axis of rotation, which is equal to OB. So one cannot calculate the sum of these two moments using the traditional method. So another way to solve this problem is to notice that the forces F1 and F2 form a couple. So the moment of the force F1 around delta plus the moment of the force F2 around delta is equal to the moment of the couple, since F1 and F2 form a couple. Why? Because they have same line of action, opposite direction, and same magnitude. Okay, so now in this case the moment of the force F1, so let me say here that the magnitude F1 is equal to the magnitude F2 is equal to F is equal to 5 newtons. So the moment of the force F1 around delta plus the moment of the force F2 around delta is equal to the moment of the couple formed by the forces F1 and F2 which is equal to F tangential multiplied by the distance d. Now here the distance d is the distance between the point of application of the force F1 and the point of application of the force F2, which is equal to AB. So in this case this is equal to 1 meter, and F tangential is equal to how much? So if this is the positive direction of rotation, notice that F1 will try to rotate the system in the negative direction, so it's minus. Either you consider or F1 or F2, both of them they will give the same result. If you want to consider F2, notice that F2 will try to rotate the system in the negative direction, so it's also minus. Well, so here we have the magnitude F, which is the same for F1 and F2. Now in this case, if this is the radial direction, then this is the tangential. F1 completely lies on the tangential direction, so no need for the cosine. Then here this will be equal to, the moment of the couple, or the moment of the force F1 over delta plus the moment of the force F2 over delta is equal to moment of the couple, which is equal to F tangential times d, which is equal to minus F times the distance d, which is equal to minus 5, which is the magnitude of the forces, multiplied by 1, which is equal to minus 5 in Newton meter. Okay, so in this case the moment and let me here write also the following note. Whenever two forces form a couple, then it is easier to calculate their sum of moments using moment of the couple, which is equal to F tangential times d, instead of calculating moment and the moment of the force F2 over delta separately, since the distance d and the moment of the couple is the distance between the point of application of F1 and the point of application F2, and independent of the distance relative to the axis of rotation. Okay, so this is it for section number 3, which is the moment of a couple. Now let's move to the other section, which is section number 4, which is given by Newton's second law for dynamics. Or let me say Newton's second law, for rotation. And here we have a large discussion. We have a large discussion to pass through. Now let's start. Okay, so here we will talk about the case of translation. And compare it in the case of rotation. Now in the case of the translation, we have defined a quantity which is the force F, which performs an action. Now in this case, in the rotation, we have talked about the moment of the force F, and in this case we need to specify the axis of rotation. Now in the translation, we talked about the equilibrium condition, which is given by the sum of forces is equal to 0. Now in the case of the rotation, we talked about the sum of moments is equal to 0 around a certain axis delta. Now in this case, in the case of translation, we have discussed the following equation, which is extremely important. Sum of forces is equal to ma. And now in this case, we wish to write here something which is in agreement with this equation. What we are performing here is called the analogy. Analogy means comparing physical quantities. So first, let us write down what is meant by analogy. Is the comparison between physical quantities which yields to a new conclusion. So in this case, if we want to continue our study based on the analogy, we know that the F is an analogy with the moment. The sum of forces is an analogy with the sum of moments. This is trivial. Now what about this equation? So how one should complete this equation? If you want to write sum of forces is equal to ma. So in order to write the rotational version, we need to write the sum of moments is equal to what? So we are not sure if the mass in case of translation will be the mass in the case of rotation, and we don't know if the acceleration will be the same in the case of acceleration. So now in order to explain what will happen, let me consider the following. Let me consider here an axis of rotation, delta, which is the center O, passing through the center O. And let me in this case consider only one body connected to the point O. So here we have a mass m. So let me say consider a solid ass connected to the axis of rotation delta passing through O through a massless rod. And I will start from the following equation, which is the sum of forces is equal to MA, in order to reach the following form, which is given by the sum of moments. Now here, let me say that this happens in, okay, so without the following assumptions. And here let me consider several forces acting on the solid S. This is the solid S. Let me consider several forces acting on the solid S. For example, one of them is the weight, and one of them is magnetic force, one of them I don't know, the other is here. We have several forces acting on the solid S like this. So this is F1. F1 in this case may represent the weight. We have another force given by F2. We have third force given by F3, another force given by F4. We don't know. Okay. So this equation now will split into the following. On the left hand side, we write the different forces acting on F1 plus F2 plus F3 plus F4 is equal to MA. Now suppose, also let me say that this distance here, let me do it this way. So consider a solid S connected to the axis of rotation delta passing through O through a massless rod of length AB is equal to D. So all of these forces have the same point of application, which is given by A. The solid S, which is able to rotate around the axis delta, is given by the mass M, and this is the point B. Let me say this is AO. Okay. Now we know that, and suppose this is the positive axis of rotation, and we don't care about it for the time being. Now suppose recall that we want to reach this form, which is related to the rotation. Now in this case, we don't know how to solve vectorial equations. The only way that we know how to solve is using projection. We are free to project along any axis that we want. Usually we project along the x-axis and the y-axis, but till this moment we didn't consider the projection along the tangential direction in such type of equations. Okay, why I'm thinking about the tangential direction? Because we know that now this is related to the tangential direction, because here it will split into the following form, so the moment of the force F1 over delta plus the moment of the force F2 over delta plus the moment of the force F3 over delta plus the moment of the force F4 over delta is equal to something that we don't know. Now in this case, this is F1 tangential multiplied by the distance t plus F1 2 tangential multiplied by the distance t plus F3 tangential multiplied by the distance t plus F4 tangential multiplied by the distance t. So this is equal to something. Now in order to reach the following form that we are searching for, then completed with the analogy, let me say here projection along the tangential direction. And here we don't care about what's happening actually in the figure, because everything that we are doing yet, it didn't involve any cosine or sine or any angle. Okay, everything till here is general. We don't care about the number of forces acting on the mass M. We don't care about their direction. The only assumption that we are making is that the forces F1, F2, and F3 and F4 have the same distance from the point O to the point, from the point A to the point O. Now projection along the tangential direction. In this case, we drop down all the vector quantities, and each vector quantity will carry the tangential direction. So F1 tangential plus F2 tangential plus F3 tangential plus F4 tangential, which is equal to M, doesn't have any projection, multiplied by A tangential. And here it's extremely important to point out that the component of A is the tangential direction. Now multiply all members and quantities by D, which is the distance of the axis of rotation from the axis of rotation to the point of application of the forces, which is common. Now F1 T plus F2T plus F3T plus F4T, all of them multiplied by the distance D, is equal to MA tangential multiplied by the distance C. Then this is given by F1 tangential multiplied by D plus F2 tangential multiplied by D plus F3 tangential multiplied by D plus F4 tangential multiplied by D, which is equal to MA tangential multiplied by D. Now so what does this term represent? It is the moment of the force F1 along the axis delta plus the moment of the force F2 around the axis delta plus the moment of the force F3 around the axis delta plus the moment of the force F4 along the axis delta, which is equal to MA tangential multiplied by the distance D. So this is given by the sum of moments around the axis delta is equal to MA tangential multiplied by D. So the first thing that we can notice is that it's not trivial to say that MA will be described directly by MA in analogy, because notice that here we have something which is different. We have mass multiplied by acceleration multiplied by distance. Now here the anticipation is not trivial. Now let's recall, because we are talking about rotation, and usually the equations of motions of rotation are given by either UCM or UVCM, okay, and in this case they are given by if the object is moving in a circular path along with the constant speed, then the equations of motion are given by theta is equal to omega t plus theta 0. Omega is equal to a constant and alpha is equal to 0. In this case they are given by theta is equal to half alpha t square plus omega 0 t plus theta 0, and we have that omega is equal to alpha t plus omega 0. We also have that alpha is equal to constant. So in both cases we have the following equations, but in general recall that we have defined the angular displacement given by S is equal to R theta by the linear speed, which is given by R omega, and the tangential acceleration, and previously we have to write t as a small t, but it's okay, which is equal to R alpha. So using this equation independent of the type of motion, okay. So now we have reached the fact that sum of moments of delta is equal to m a tangential multiplied by the distance d, but we know that a tangential is equal to r multiplied by alpha. Now let's recall, what does r represent? R in this case is equal to d, which is the distance from the axis of rotation, or the radius, which is the distance from the axis of rotation to the mass itself. So in this case let's replace d by r, So let's say that d is equal to r equal the distance from axis of rotation to the object, in this case, or to the object, or more precisely to the applied force. Let me say to the applied force. Which is the same to the object. Now in this case, so we have that the sum of moments around the axis delta. Now here from this one, A tangential, okay, it's equal to R alpha. So it is given by sum of moments is equal to m r square multiplied by alpha. And this equation is given by the Newton's second law in the case of rotation, but it's not the complete one. Let me explain why. So if you are talking about the sum of forces is equal to ma, and we want to compare it with another equation, we need to compare it with the sum of moments around delta is equal to m r square multiplied by alpha. Now, okay, the force is being in analogy with the moment around an axis delta. The acceleration is being compared with the angular acceleration, which is alpha. Although they are not the same, here let me make clear they are not the same. We know that this A is the total acceleration, which splits into two accelerations, the tangential acceleration or the normal acceleration, even AX and AY. Okay, here I'm just comparing. Notice that I have placed an arrow and I'm not saying an equality. Okay, what about m? M is compared to a new quantity which is given by mr square. This quantity we will call it the moment of inertia, which is given by I. So now in this case, the sum of moments around an axis delta will be given by I alpha. Let me define what does each quantity represent. The sum of moments acting on a solid S alpha is the angular acceleration, and it's unit given by radians per second square, and I is the moment of inertia of the given solid. And the unit of I is given by, let me check here, if this is kilogram and this is meter, then meter to the power 2. So this is kilogram a meter square. Okay, and here let me write the following important note. The expression of I, it depends on the solid, on the shape of the solid, and by this we mean the distribution of mass around the axis of rotation. So the distribution depends on the shape of the solid. the distribution of mass, as well as the position of the axis of rotation. Okay, now let's consider the following table that gives different expressions of the moment of inertia. So I know that the story will not be clear until we solve several exercises on this topic. So here let me say that the table consists of 4 columns. So in the first column they are telling me the shape of the body. In the second column they are telling me where does the axis of rotation pass through. In the third column they are giving me a figure, and in the third column they are giving me the moment of inertia. So here the moment of inertia, we are talking about I. So this is I equal, I equal, I equal. So where do we use the moment of inertia? Because if you are applying Newton's second law of rotation, which is given by the sum of moments around the axis delta and the system is rotating, we need to write I alpha, and in this case alpha I depends on the shape of the body. So let me consider the first case. If the body that we are considering is a ring, which is a hoop, so a ring is like a disc but is empty from inside. There is no solid inside. So this you can consider it as an empty ring, empty disc. So first of all we need to specify the axis of rotation. The axis of rotation is passing through the center of the hoop. Okay, now you can ask me if the ring is empty. How come the ring is rotating around the axis passing through its center and the ring is empty? How could it be connected to the axis of rotation? Suppose it is connected by massless rods, like in the case of the wheel of a bicycle. Okay, so these rods that connect the hoop with the center are considered to be massless. So in this case the moment of inertia is given by what? Is given by given by mr square. Now the same ring that we are considering, the empty disc, instead of being rotated about an axis passing through its center, we can consider the axis of rotation passing along its diameter. So about any diameter. So this axis of rotation passes through 3 points, 2 points along the circumference and 1 point in the center. So it passes along a diameter. In this case the moment of inertia changes. Now it's given by half mr square, because this is related to how the mass is distributed around the center. Now if we are talking about a disk, then the moment of inertia around an axis passing through the disk is given by half mr square, in which r is the radius, m is the mass of the disk. Here r is the radius of the ring, and m mass, let me write them here. M is the mass of the disk, r is given by the radius of the disk, now here r okay, let me say m is the mass of the hoop, and r is the radius of the hoop. Here similarly. Okay, now if you consider the fourth case, now this list it can never end, because you can consider any geometrical shape that you can imagine. For example, you can consider the human body, and you try to calculate its moment of inertia. Now there is a certain method in order to calculate this moment of inertia, but we will not consider in this case because it's a bit difficult. Now we will only consider some moments of inertia of some geometrical shapes that we will encounter during the exercises. Now let me consider the fifth case, which is a cylindrical shape. Now if the axis of rotation is passing like this, we can for example consider the axis of rotation passing through the diameter like this, but we'll consider only passes through the center of symmetry of the cylinder about its own axis, then it's given by mr square. In case if it's passing through the diameter of the disk, it's given by half mr square. Now if it passes along the center of the sphere or the diameter, then the moment of inertia is given by 2 over 5 mr square. And in case if it's passing through and about a tangential axis of the sphere, then it's given by 7 over 5 mr square. Now if we are talking about long thin rod and it's passing through the center, then it's given by 1 over 12 ml square. In this case, L represents the length of the rod. Here R is the radius of the sphere. In the case of the cylinder, R is the radius of the cylinder. R in this case is the radius of the sphere. R in this case is the radius of the sphere and is independent of the distance between the radius and the axis of rotation. And finally, for the rod passing through the extremity is given by 1 over 3 ml square. Okay, so yet a lot of things that we can ask regarding this topic, and we can discuss several stuff. Okay, but just to make stuff, okay, let me solve. Okay, no, let me also consider the following note just as a final topic for this video. Now, because now the terminology moment or the word moment appears in several places, so let's also make the following important note. Now, whenever we say moment, now at least we mean three things. We either talk about the moment of a force, or either we talk about the moment of inertia, or either we talk about the moment of a couple. Okay, so the word moment alone doesn't mean anything except for rotation. Okay, so we are talking about the rotational version of the force. We are talking about the rotational version of the mass, which is the inertia, and we are talking about the rotational version of the couple. Okay, so now in the next video, I hope that I will discuss what is meant by inertia, what is the real meaning of the mass, and we will solve some exercises on the following just to illustrate what is meant by the moment of inertia and how can it be included in the Newton's second law for rotation. Okay, so that's it for me in this video, guys. In the next part 8, we will discuss more regarding Newton's second law for rotation.